physics and nature in general is built on two principles. To this day, neither of those two principles have been what? Have been violated or have been completely, or sorry, have been contradicted. Okay? So the first one is this one. For any system, and the word system always means group of interacting particles. By the way, sorry. By the way, the word interacting is very important. The particles have to interact somehow. If you have a bunch of particles that do not interact in any way, gravitationally, electrically, magnetically, you don't have a system. Because to each particle, the others do not exist. Okay? No. It has to be interacting. Okay? So a group of interacting particles, the momentum. Again, is that today's topic? Momentum? No. Momentum, we will keep it to next week. Okay? We have to finish energy first. The momentum of the system is what? Conserved. What's the second principle? Literally the same wording, only one word changes. Instead of momentum, we talk about what? Energy. The total energy is what? Is conserved. Okay? By the way, everyone, technically, I mean, you don't have to write it. You will understand as we go along today. It should be total energy and total momentum. Okay? What if one of those systems, sorry, what if one of those principles is broken? Well, pigs could fly, which basically means it's impossible. To this day, not a single phenomenon or system in the universe, doesn't matter where, on Earth, deep space, inside of the atom, not a single phenomenon violated these two. And that's why whenever absolutely any engineer or physicist starts with what? With analyzing a physics problem, the first thing they impose or force the system to go by is that the momentum has to be conserved and the energy has to be conserved. Okay? Has not been violated to this day. Okay? All right. I like to teach what? A few different ways of understanding what conservation of energy means. Okay? Like a few different ways of saying it. Okay? All right. So let's go to the next slide. All right. I believe you have a few to fill. Yes. Okay. So I'm going to give you, everyone, listen up. Let this sink in. I'm going to give you 4 different ways of literally saying the same thing, but it sounds different, to give you 4 different ways of understanding. At least it made sense to me when I took the course 25 years ago, what conservation of energy is really about. So the statement of the principle, sometimes called the law, because it is a law of conservation of energy, is, okay, here's the official way of saying it. There we go. The sum or addition or combination or total of all the energies of the system, like whatever whatever in the chart that could apply to the system, thermal, gravitational, nuclear, chemical, whatever, has the same value at all times. Has the same value at all times. Okay? By the way, question. How many people here heard of, okay, how many people are doing chemistry or did chemistry? Okay. How many people have heard this expression in chemistry? Closed system or isolated system. Exactly. The system needs to be what? The system needs to be closed, which means what? Nothing could come in and nothing could what? Otherwise, you don't have what we call a sealed system, and things could leak in or leak out. Okay? So the sum or total of all the energies of a system at all times must give you exactly the same number or the same value. Okay, this is a very dry way of saying it. So let's actually say it in a few different ways to really give it some life. Here's my first way. Okay, so other ways this could be understood are, number 1, the addition of all the forms of energy of a system at any given moment must give you the exact same value. What's up? Oh, yeah, sure. Oh, you have. It's only one copy. Yeah, it's only one page, two-sided today. Okay, so the addition of all forms of energy of the system at any moment from the beginning of the experiment till the end of the experiment must give you the same value. So that's one way. By the way, this way is very similar to the first way, right? Because look at them. Addition means sum. All forms of energy means all energies has the same value at all times, at any moment. So this is really almost the closest way to say the first statement. Here's the second way. The only way that things could add up always to the same exact value is for all the forms of energy to keep doing what? Giving to and taking from each other to balance themselves out. I like this way because it's actually the way I've been thinking about energy ever since I took physics. And basically, it is why I'm a physics teacher. This made so much sense to me. So always think of it this way. It's a what? It's a balancing act. It's a balancing act. Something loses, another part what? Gains, and vice versa. Okay? So energy forms must give to and take from each other to balance themselves out. Okay? All right. Number 3. This is probably the most famous way, which is this. Energy could neither be what? Created nor destroyed. Energy of a closed system, could never be created nor destroyed from vacuum. Okay, this is the most famous and the shortest way to say it. Okay, the 4th way is the most famous one, or the most popular one among astrophysicists or cosmologists. Okay, who does anyone know who was probably the most famous cosmologist? Hawking, Stephen Hawking. Yes, cosmology is basically the study of the early universe, okay, which is very related to astrophysics, but not exactly the same thing, okay? So cosmologists, which really helped them popularize the, the Big Bang theory, is this. A system begins with a fixed amount of energy and is stuck with it forever. No more, no less. Why is this popular among what? Among cosmologists and astrophysicists? Because that's basically their argument that what? That the universe, at the very, very, very beginning of its what? Of its basically of its beginning, started with one value of energy. Obviously, the energy was what? But was it infinite? Question for you. If you have an infinite amount of money, do you need to save money? No. If you have an infinite level of something, there will be no need for the word what? For the word conservation. Conserve means what? At the end of the day, something has to be infinite or finite. Finite. No matter how what? No matter how huge or vast it is. And that's basically what their argument with what? For the Big Bang, for the expansion, and again, the what? The reduction or the spring motion of the universe. Again, this is just insane advanced astrophysics stuff, but it's basically what? Every single day it gains more what? More proof. And every 5 or 6 years, an astrophysicist wins a Nobel Prize for either a theoretical prediction that's been verified, or for what? An experiment that verified what? Theoretical prediction, like the discovery of the gravitational wave that was awarded the Nobel Prize in 2016. Yes. Okay. All right. These are the 4 ways. Okay. Think of it anyway. All of them mean the exact same thing. This is my favorite one. Energy forms must give to and take from. You'll see why. Okay. The best way to understand this is to do a quick example. And I'm going to give you a specific slide for that. All right? There you go. Same one from 3U. There you go. Okay. So now, everyone, the reason I gave you such a large slide just by itself is because I want you to do all the calculation. Everyone, you have a choice. Can I just use yours? You have a choice, everyone. You can do the calculation, like divide this into 3 parts and do the calculation under here, under each, I call these bar diagrams because they are bars. Or you can just do it here as like 3 different levels. Okay? It's completely up to you. All right? I'm going to do them right here. You choose whatever works for you. So the question is simple. Okay, what do we have here? What situation do we have? We have what? We have a baseball. Now, is it moving down or moving up? So it was moving down until it got what? Hit by a baseball, came to decelerate, stopped, and then was what? Reversed back. Okay? So the question is always, by the way, I have T, you have what? M. Okay, it's the same idea. T is total. M, does anyone remember what's M from oh my God, grade 11 physics? What? Again? Yes, everyone. When you only combine kinetic and gravitational, you still can call it total, but it has a special name. We call it what? The mechanical energy of a system. Okay? So don't change it to T. Keep it as M, because actually that's why I intended on doing today. Okay? All right. Hold on 1 second. Okay. Okay, everyone. First of all, right there, is that object, everyone listen up, Is that object moving? So right there, what energy does it have? Number two, right there, is that object elevated above the surface of the Earth? So what energy must it also have as well? Gravitational. Great. So I need to give you what? So can someone tell me what's the equation for EK? Very short one. Half m. So I need to give you what about this ball? To calculate, no, you need to be given the mass and the speed. Okay, what's the equation for EG? Three things multiplied together. M, G, H. I'm going to give you the mass, but now for the EG, you need to get what? Sorry, I need to give you what? What do you call it? Not height. Elevation is a more proper word. Okay, so here are the numbers for this problem, randomly. So I want you to put, okay, go ahead. The initial elevation or the hitting elevation of this ball is 1.5. Actually, let's make it 1.50, so we can keep it to how many sig figs? No, it's already 2. Let's just add one more. So everyone, make it 1.50. 1.5. Sorry, 1.50. Not yeah. 1.50. Okay, in meters. So everything is standard. Number 2, how much speed was it given right as it left the bat? 19. So this also needs to be made into 3 sig figs. So what do you make it? 19 point, and you add a precision 0, so it becomes 19.0. All right. What else do I need to give you for the equations to work or to be fully evaluated? Again, mass. Okay. We can look up the mass of a baseball, but let's say a baseball has a mass of, let's say, for example, 350 grams. 350 grams. That needs to be converted to what? Kilograms. So everyone, under that green box in your note, just write m equals 0.35 0.350 kilograms. So m equals 0.350. Why 0.350? Because I also want it to be in 3 sig figs. All right. Okay. When this ball gets hit and it leaves the bat, does it move forever in a straight line? Only in what? Only in, not vacuum, but exactly. Remember, everyone, is vacuum and deep space the same thing? No. Deep space is the what? Is the absence of everything, including both air or a medium and gravity. Vacuum only means the absence of what? Air. But you still have what? You potentially still have gravity. So the only thing we're eliminating here is air, so there's no air drag. But there has to be gravity, which means what kind of motion would this be subject to after leaving the bat? What kind of motion did we do at the end of the kinematics unit? Goes like a perfect parabola in vacuum. Projectile motion. You see, I can tie this problem also to kinematics, but I'm not going to do that today. All right. Okay, here's my question for you. Right here, if you have these 3 numbers, can you calculate the EK of the system? Sorry, not of the system, of the ball. Well, the ball right now. Great. Can you also calculate the EG? How can you calculate? Sorry, yeah, the EG. Can you also calculate the EM? What is the only thing you need to do to always get E mechanical? What do you just do with the 2 numbers? Every single time you have the 2, just add them up. Okay. So the first thing we're going to do is what? Under this diagram, we're going to calculate what? EK, EG, and then EM. In any order, EK first or EG first, doesn't matter. You have to do both. Okay, so let's do that. So EK equals half. The mass is 0.350, and the V is 19 squared. Equals. Okay, help me out. What's this number? I would recommend you square first, and then you multiply. Like basically go from right to left. That's the easiest way to do bed mass. Go from right to left, because usually it's this one that appears at the end, the brackets and the exponents, which has to be done first. Yeah, Ammar, what'd you get? So Ammar got 63.17, correct? All right, so 63.17. In what unit? Work and energy are always measured in joules. Good. All right, next, EG. E, G. Mass. Then what? Is it negative or positive 9.8? Yes, remember, negative only with kinematics. But when you do EG, you always just need the gravitational strength of the Earth, not the direction. So 9.8. And the height is, elevation is 1.5. Okay, who's got this? By the way, it should be a much smaller number than what? Than the 63, because look at nothing is squared and lots of decimals. Yes. 5 point, 5.4. Oh, 145. Okay. 145. Also in what? All right. Yeah. Again, intermediate steps, and now we're just gonna add up. Oh, it was okay. 175. Okay. Remember, for intermediate steps, you only need how many more than the sig figs you need? Just one. So you could have kept it as 1/8 if you wanted. Okay. All right. I'm gonna change this one to M, so to be consistent with your notes. Okay. So what's EM? Yes, the addition of this one. I'm sorry. The addition of this one and this one. So what's the answer? 68. So if you add 175 to 145, you get what? 0.32. However, now we have to make it how many digits? 3, because that's basically the final answer for this one. So what would it just be? 68.3. Also in what? Okay. Do you remember what we did with the bars in grade 11? Again? Exactly. You fill them in. And you, again, does the fill need to be exact? But does it need to be representative of the magnitude? Yes. So obviously, which number is much bigger than the other? Which bar always has 100% no matter where the system is? Exactly. Because remember, there's no underflow and there's no overflow. That's the whole idea of conservation. You never leak out and you never miss in. So that means I need to pick a random height for the K, a random height for the G. Okay. Do I just pick random heights for the K and the G, or do they have to be consistent in a way? How so? I agree. What's the second thing as well? Exactly. Whatever is left on top of the EK is exactly the what? The what? The EG. Can be lower because then you have underflow. Can be more because then you have overflow. So roughly, again, you never lose marks unless the gap is way. So there's so much discrepancy between the gap here and the fill here, like this. There we go. So that's it. If I chose this, I have decided this much must be here. Because this thing has to be perfectly up to the what? Up to the top level, like up to the brim. No more, no less. And I'm always going to do this whenever I have a bar diagram. I'm always going to put a plus and then equal. To always give me the what? The confirmation that those two need to add up to that. Okay? All right. So that's the initial what? The initial or the beginning observation of the system. So we go with that, and we know it's going to go in a perfect parabola of a what? Of a projectile motion. All right. Where's the next most interesting instance? By the way, say again? Exactly. Obviously, there's nothing special about. Obviously, there's something special about this. There's nothing special about all this until you hit right here. Okay. What do I need to give you here? I need to give you one of two things: either the speed at the maximum level or the elevation at maximum level. But depends. If I give you one, I'm going to ask you for the other. Which one do you remember I gave you for grade 11? You remember? I gave you the elevation at that. There we go. So go ahead and just label that as 4.2. Above the ground. Our reference is the ground. Okay? Again with the bars. Sorry. So I'm just going to put a divider line here. There we go. Okay. Everyone, question now. Even though I did absolutely no calculations for the middle step, which bar could I fill right now? Which bar never changes? M. There you go. So go ahead and just fill this one all the way up. Okay? Once you know the M once, do you always know it? And that is always the central idea of today's lesson. If you get the energy mechanical or mechanical energy once, guess what? You know it for the rest of the experiment. Which means technically now, which one should I write at the top here? Which one do I know now? Great. So you start with it. EM is the entire energy of the ball at all times. EM equals, sorry, capital or small, let's make it capital, is 68.3. Okay. Since you're given the elevation, which energy can you calculate right now? Gravitational. So let's do that. So EG equals M G. Oh, sorry. What? My bad. Not 38, 35. Mm-hmm. 3, 5 times 9.8 times 4.2. 14.406. Also in what? Can you compare that EG to the first EG? Is it the same, lower, or higher? Does that make sense? When you go above, sorry, when you go more above the surface of the planet, do you have more potential to fall or less potential to fall? More, which means what? If you get released, you have now more energy to what? To convert to kinetic. So that makes sense. Okay, how can I do AK now? Remember, I have some money and I only can give it to two people. So that all of it, which means if I give a person A some money, what's the only possible choice for person B? The remainder, the leftover, the subtraction. You got it. So EK is nothing more than that. Subtract this. That's why this is a very organized way of doing your solution. You're telling yourself, this is the max, this is the whole bag, this was given to one bar. The other bar has to claim the rest. So EK equals 68.3. By the way, if again, just so you know, we still have more calculation to do. So it might be a good idea now to do this calculation up to here, like up to the one we're going to finish right now, and then do the rest maybe on the back side or maybe under the curve, like right here, whatever works for you. So 68.3 minus 14.606. How much? Sorry, 406. How much is that? 4, 53 point in what in? Does that really help me out understanding the motion of the sorry, not the motion, imagine the motion of the ball? No. By the way, when you look at a car outside, are you interested in its ek? You're always interested in its what? Exactly. Ek is fine, but as a physical picture, you just need to know how much motion it's got. So we need to calculate the v here. Can we calculate the v? What's the equation for ek? Half mv squared. We know the ek, we know the half, we know the mass. We can definitely calculate the what? The v. So I'm just going to, so let me actually do it here. So, okay, I'll give you the quick equation, everyone. You can rearrange for sure, but the quick equation is this. V equals square root, because it's been squared, I need to reverse it by square rooting it, 2 ek divided by what? Sorry. Okay, I'm going to do the quick derivation here. Everyone, do not copy it. I just want to show you how this came about. So obviously, it's ek equals half mv squared. As we said yesterday, you multiply this by 2 and this by 2 to cancel the half. So 2 ek equals mv squared. And since you know you want the v squared is equal to 2 ek divided by m. And then what happens? You square root the whole thing. That's where that equation came from. All right. So all you have to do now is plug these numbers in and get the what? Get the speed of the ball at the top elevation of the motion. So multiply EK, this EK by 2, and divide by M, which is 0.350, and get the square root. Who's got this? Come on. Let's hear two numbers, or the same number twice. Yes, Amar, what'd you get? You got 17.54. How many people got that number? Does that make sense? Look at the problem. Does it make sense at that moment to have a speed of 17.54? Or in general, does it make sense to have a speed less than 19 there? Why? Give me a few arguments. One per student. Okay, Josh, what's your argument? Just one. Could be mathematical, could be physical, could be whatever you want. Say again? It is technically going up. And if anything is going up without an engine of its own, what must happen to its motion? Speed up or slow down? Decelerate. Even if it's going in a what? In an arc, in a projectile motion. So that's one argument. What's another argument? Ahmed? So it's going against gravity. There's another argument you can think of. Ammar. Exact. This bar stayed the same. This bar went what? Which means this bar has to what? And if EK go down and the mass doesn't change, what must go down? Exactly. The velocity must be going down. Yes. Thank you. Yes. Conversion. Now we have the what? The switching of the forms, but such that everything is what? Is a balanced act at the end. Perfect. See, it's through telling yourself the whole thing as an actual story, everything starts to make sense. So obviously now, I randomly chose to what? To bring this one from down, from here to here, which means now this gap, even if it's exaggerated, who cares? Has to be whatever is left here. There we go. Oh, sorry, what was the answer? I forgot to write. 17 point. So 3 sig figs, 17.5 meters per second. Okay, come on. What's the last interesting instance of this motion? Oh, okay, hold on. Yes, you all know from grade 11 that whenever we do this problem, I always mention to you that, and we always have this debate, what's the speed when it hits the ground? Okay, when you say when it hits the ground, technically, what's the speed? 0. But would that make any physics problem interesting? Absolutely not, because everything, once it hits the ground, it has to decelerate to a 0 speed before maybe it bounces up or something. But at least we know the eventual speed is 0. But what do you think I really mean? When exactly before? So what's the height that we're interested in? Like how high above the ground is it? Okay, so imagine if I left you to your own devices and I said, you guess the height. You might guess what? 1 millimeter, right? Like just above the ground, right? Ragad might guess, no, I can go closer. I can go 1 micrometer. Ammar might go, I can get what? 1 nanometer. You might go 1 picometer, femtometer. Do you think that's practical? But, okay, let's be honest. By the time you approximate your answer to 3 sig figs, do you think I'm going to see any difference in your final answer? Absolutely not. Not with what? Not with keeping to 3 sig figs. So what practical height should we, not official, practical height should we really assume as 0? How many people are doing advanced functions in calculus? What's the first thing you study in calculus? Limits. What's limits? You get what? You get as close as you can, but never what? You never touch. Do you see what I mean? Literally, that's exactly what we're doing. So obviously, since the whole thing is approaching a limit of 0 height, just what? Slap a 0 to the height, and then what? All the energy technically goes to which bar now? If there is no height, what bar goes all the way down? Gravity, which means which bar picks up all the slack and goes all the way up besides EM? EK. There you go. So remember, and by the way, just so you know, my very first test I gave for energy conservation 12 years ago at Weevil, I gave the question, What's the speed when it hits the ground? 2/3 of the class said what? I had to give everyone full marks for that. I had to, because I'm like, why is it? I'm like, wait a minute. You technically said what? When, which means I had to give everyone 0. Guess what I did for the second term? Changed it to what? Immediately before landing or I had to, because then you cannot put 0. Sorry, you cannot put 0 as a speed, but you're encouraged to put 0 as a what? As an elevation or height. Perfect. Okay. So there we go. Okay. So the question now is, right before it touches, what's the maximum speed it builds up to? Well, again, which bar has no change? M. So go ahead and fill the M bar. Okay, listen up. Now, the eternal debate. How much fill should you put for the G? How many people say nothing? How many people say a small sliver, since you technically did not touch yet? Do you think both of these ways of thinking are correct? Yes, from a mathematical standpoint, it is 0. But from a physical standpoint, it is not what? It is not 0. But either way, is it the correct idea? Yes, which means whether you put a very small, it has to be a small thin line. Whether you put a very small thin line or nothing, I have to give you full marks. Okay? So I think in my slideshows, I always go for what? For a very thin gray line. So everyone look. Obviously. And again, if you're doing a thin line here, you also have to remove a what? You have to remove a thin line from the what? From the top of that. But these are approximate diagrams. So everything will be given full marks. So everyone look. Just focus here now. Right here. Aha. Thin line. Again, you can put it on the diagram. You may not. It's completely up to you. Both ways are correct as far as thinking is concerned. Okay. Still, which energy do we know for sure right now? Right now, which one should we write first? You know it once, you know it all the time. So go ahead, EM. EM equals the 68.3 joules. So practically, what's EG right now? EG. Yeah, it went all the way down because it's almost at what landing level. So EG is a practical 0. And there's no need to put like the wavy equal. No, just make 0. That's it. Which means EK has to be how much now? All of it. If you have two people and one of them gets no money, the other person has to get all the money. So EK must be all of it. What do we do now? Do we still reuse the same equation from the second instance? 100%. The only difference is my EK now is all of it. Sorry, all of EM, I mean. My question now is, even before you solve, could you be 19? Why do you have to be more? Again, what arguments? Ammar, give me one argument, and then you get to say yours. Mhm. Question for you. Is there another moment where it comes back to exactly 19? Exactly. Because parabolas are always what? What do you call something that could be divided into two identical halves, like your face? Symmetric, which means what? Whatever happens here, this bar diagram has to be perfectly repeated where? So what happens in this very small elevation? It's what? So is it going against or with gravity? So what's happening to the speed? Slightly, it gets what? It gets faster. There you go. Yes, exactly. Again, symmetry. Symmetry always works for what? For parabola. Okay, so now let's do this equation. So V equals another 2ek. What's my speed now? What's my speed now? By the way, with sometimes, depending on how much extra speed, you might get a 3 sig figs, you might get the same number. You know it's not, but that's what sig figs do sometimes, is that they give you an impression that, oh, it went back to the same speed. It didn't. It just rounded to the same speed. So who's got this? I don't remember. 19 point? How many people got 19.75? So according to 3 sig figs, how much? Done. That's it. Welcome to conservation of energy. If you always think of it as a bar approach, you might make numerical mistakes, but you will not have any understanding issues. It's all a balancing game. Now, my question to you is, what if I had more energies involved in the system? What's going to happen to the number of bars? Yeah, I'm just going to have what? More bars. Now, does that make the system easier or more complex? Why? So my question to you is, everyone, I have $100. I want to give it to two. If I give you 70, I have to give Rod how much? Because I am allowed to leave with nothing. Okay, how about if I want to give it to three people? And I gave you 70. Is there only one way I could divvy up between you two? Or one way? How many ways? Okay, with money, it's not infinite, right? Because you can break it down to the what? You can argue to the cent or to the 5 cents now, right? But with energy, what do we have? Energy is discrete or continuous, which means what? There's an infinite what number of choices, even if I fix what Janan's money and I go with these. What if I add more? What's going to happen now? But do you see what I mean? But I could still what? I could still say you get 70, you get nothing, which means now it's a two-bar system. Do you see what I mean? That's why the more bars, the more careful you have to be about which ones could change and which ones may not. Okay? Good. All right. So now let's do what? Let's do this one. Real quick. We always get just to one practice worksheet. And before you leave, I'm going to give you the other two. All right. I think we're good. Okay. Okay. Is it the same that you have almost? Yeah, the diagram looks slightly different because that's for my grade 11, but it's the same idea. Okay. Um, J Josh, go ahead and read the question for us. Everyone, listen up. I want to finish in like 10 minutes to give you time to just relax. So go ahead. Okay. Go ahead. So in a way, it's kind of like the baseball problem. The only difference is this projectile motion. Just right straight up, straight down. You go on. Yep. Perfect. Okay. Do I know the mass of the ball? Do I know the initial elevation? Do I know the initial launching speed? Great. I can know everything about the initial instant. All right, let's do that. By the way, I ordered them this way. You could have done the EG and the EK first. Sorry, I mean the EG first. Okay, let's start. So half, go ahead. Half mass is 535, which means it has to be what? In kilos. So point 0.535 times 16 squared. Who's got this? One shot. Come on. And 256, 16, 128, 100 something? No, no, no. What am I talking? Yeah. Oh, really? Okay. 16 is 256. Yeah, you're right. 68.48 in joules. All right. EG, point 535, 9.8, 1.6. You guys have them all to three sig figs, right? Yeah, okay, because my diagram is old, so it's only two. All right. What would this be? Very small number. 8 point. All right, 8. Great. Let's add them up. What's my EM? So it would be 76. Is it? Yes, 6, because it doesn't make 77. Point. Hmm? So 9, right? Okay, everyone, 76.9 in joules. Okay, let's do the bar fill. Obviously, you always start with making 100% for the math. Sorry, for the mechanical. So everyone go ahead and mechanical gets a full fill. Obviously, look at the huge difference in the numbers. 68 for the K, only 8 for the G. Whether in what just make it representative. So I'm just gonna go from here, like up to here, and that means only up to here. That's it. Done. Oops, my bad. Come on. All right. Okay. Done. That's it for the first instance. Now keeps going up and up and up and up and up. How what is so special about reaching maximum height or about hitting maximum height? What happens at any maximum height? Okay, now it depends. If it's projectile motion, is the speed 0? Only the vertical speed is 0. But when it's perfectly up, what physically happens at the top? Legit speed is 0. Which means at that moment, which energy is instantaneously 0? EG or EK? No motion, EK is 0. Perfect. So right there, just put 0 joules here. Don't even show me a calculation, because the calculation is going to have you multiply 0 squared. So I'm a big fan of shortcuts as long as they know you know how they happen or why they happen. So everyone, 0 joules. And I want you just to write what? Stops. Just to give yourself an understanding of why that is a 0. Which one do we know either way? Which one, if you know once, you know all the time? E mechanical. So everyone, E mechanical. Which would be 76.9. So what's the only left out choice for EG? All of it, because the other one claimed nothing. 76.9. Okay, so the question now is, how high above the ground does it stop? What equation am I going to use now? The EK reverse equation or the EG reverse equation? The EG. EG equals what? MGH. But I want the H. I called it H max because it is the max height. Exactly. Everyone? So instead of EG equals MGH, you need to divide the EG by the MG because you need to solve for H. So this is equal to EG over MG, which is 76.9 times what? The 0.535 times 9.8. Who's got this? 14.7 in meters. And then what do you still add to it? What do you still add to it? 1.6. No, you don't. Trick, huh? Why do you think you don't need to add the 14.7? Is this a kinematics equation? Sorry, right now, are we doing this with kinematics or the energy? Everyone, kinematics or energy? When you do energy, what do you always have to decide on? Your what height? Your, not original, what was the name we used in notes? Reference height. What's my reference height? Which means, does that 14.7 already includes the ground? Yes, it does. Never fall into this pitfall. Never have your ground level as reference and still add what? But what if you had to do this problem using kinematics? Do you even care about the 1.6 when you do the problem? By the way, how many people see how we can do this completely using kinematics? How so? What if I asked you what's the maximum height above the ground? and you didn't remember how to do it with the energy approach. How could you do this one using kinematics and still get the full marks if it was a multiple choice question? Because then I'm not going to know how you did it. What kinematic information do you know about the ascending trip? Come on. Just look at that part. Forget this. Just from here to here. Initial speed is what? 16 positive, because we're gonna say that positive is up. That's one kinematic information. What's the second one, Ammar? Negative, pulling down accelerations to negative 9.8. Okay, 2 things done. 1 more to go. Final speed is what? Is 0. But when you solve for the distance now, are you gonna get the full thing or just the traveling distance? What do you need to add to that? Now you're gonna add the 1.6. So different methods give you what? Do they always have to give you identical answers or consistent answers? Yeah, identical might be the case sometimes, but you always want things to be what? Consistent, which means if you put them together, they make sense. Awesome. All right. So obviously, can someone tell me what's the bar fill for the top? Should you put anything in the EK in the top? We said it comes to a perfect what? Halt or stop, which means right now we are saying it's not an approximate limit approach, it's an exact what? Which means how much fill should be for the EK? None. Nice. So all of the ET and the EG, sorry, the ET and the EM should be the same. So go ahead, and this should be all of it, and this should be all of it. Okay? Comes back down. What do we have? My question is, obviously, what landing or pre-landing speed, I should say, what pre-landing speed does it have? Okay. By the way, can you see how we can do this one also with kinematics? Yeah, but it's a reverse situation. My initial speed now is 0. My 9.8 is my acceleration positive. And how much is my full traveling distance? 14.7, the full height from the ground to the top height. But I don't want to do what? I don't want to do kinematics. I could check with kinematics, but I want to do it with energy. Okay. What energy do I know out of these right now? Always EM. All right, so 76.9. Did it touch the ground yet? If you say yes, you're right. If you say if you say yes or no, it's acceptable. So that means choose to put the sliver here or not. Up to you. So I'm gonna put the ET or the EM full and the EK full, and we can put just a line here. If I can do that, yes. All right. Practically, which one of those E's is a 0? G or K? Practically. G, because it almost what? Has no height. So 0 joules. Which means EK claims the entire thing. Which means VF is the square root equation. Square root of 2 times 76.9, all of it, divided by the mass of the ball, which is 535. I know one thing. It must be bigger than what? Has to be. It repeats back 16 at the same height again, but then it falls a little bit short. Sorry, it falls more. So according to our sig fig situation, it should be what? 17 point. Because remember, 17 only is 2 sig figs. So this should be 16.95 or 17.0 meters per second before decelerating to 0 very quickly. All right? And that is how you should always be thinking about what? Energy conservation. It's a balancing game between at least 2 bars or more. We're going to do more next week for sure. We're going to add elastic because we're going to do things with spring. We're going to do a lot of things with springs, and springs always have elastic energy because they store energy and release it, whether you push on them or pull on them. Okay? That's it. So I'm going to give you the other 2 worksheets now. Again, not to be handed in, just practice. Oh, sorry, I forgot there was a part B. My bad. What is part B, everyone? Or part C? Part B, yes. Fine. Okay. And I told you using what? Is there any way you can use energy to find time? Ask yourself one question. Is there an energy equation that's got time in it? No, you can't. So that means what? You have to resort to something else. Obviously, what's the something else? Kinematics. Okay. To do what? To ascend or descend? To descend. Okay. What information can we use? We have acceleration. By the way, shoot for as many exact things as you can. Acceleration is exact. What else? Initial is 0. Problem is, you're stuck with what? You're stuck with either using what? 14.7 for the full distance traveled, or final speed of 17, or even if you go back to 16.95 for that. You have to use at least how many approximate values? Once. Okay, you know what? Let's use 14.7. Let's use 14.7. And by the way, why do you think 14.7 has slightly lesser error in it than uh, 17.0? Yeah, go ahead. There, there, you're right, but there's another reason. The 17 itself depended on another approximate, right? The only way we could get 17 is by using what? Which itself was what? Was an approximate. You see what I mean? So the lesser approximate that fit into the system, the more you should use them. Okay, so we're going to use what? We're going to use VI. We're going to use acceleration. And we're going to use what? Distance. And we need time. What's missing from the list? What's missing from the list? Hmm? What equation 1, 2, 3, 4, 5 does not have VF in it? 3. All right, so everyone, I'm just going to do it here. So what's equation 3? Delta D equals VI delta T plus 1/2 A delta T squared. What's the good news about VI in this descending trip? 0. This thing is completely written off. So delta D is 14.7. Half is half. A is 9.8 positive. Of course, positive. Otherwise, you're going to have to square root a negative for time, which can never happen. Delta T squared. So delta T is equal to the square root of 14.7 divided by half of 9.8, which is the infamous 4.9. By the way, everyone, now do you know why a lot of your grade 11 and grade 12 functions problems had 4.9 in them? Remember your rocket problem in grade, yeah, they always had 4.9. You always have 4.9 in the quadratic. It came from here. It came from projectile motion or the kinematic equation with acceleration due to Earth. Who's got this? In seconds, my guess, 15 to 1 point something. 1.7, 1.6. Has to be 1. Because this is very close to 15, and this is very close to 5, so it's the square root of 3. 1.7. Give me one more. Oh, it is, because 9 times 3 is 27. You're right, it is a perfect root 3, which is 1.7. So in vacuum, with no air drag, it should take 1.73 seconds to descend from top to bottom.